So zero equation doesn't mean that there is no equation. So what we mean by zero equation is there is a zero transport equation. Okay, we are using an algebraic expression here. So zero equation implies zero transport equation. Model. Okay, so this transport is omitted in the form. So zero equation model means zero transport equation, and then we are only considering only algebraic expression is used. Okay, and there are many models under this category of zero equation. As I mentioned in the course outline in the beginning, I will not discuss every model that is present in the literature. I will only give you one particular model under each class. Let's say zero equation, I will discuss one particular model. Go to one equation model, two equation model, like that. So I will give one example and I will tell you how this model is built. So there are many popular models here. So one particular example is called what is called a Prandtl's mixing length model. Okay, an example. Prandtl's mixing length model. So what they mean by a mixing length, I will discuss here. So this idea comes from, if you recall, the turbulent boundary layer itself. It has many sublayers. So you had, for example, if you recollect, this was the wall. So you had a region called linear sublayer where, and then above you had an inertial sublayer, right? So in the linear sublayer you had u plus equal to y plus, and far away you had inertial sublayer where u plus is a function of y plus again, but it was, the function was basically logarithmic of y plus in a log-law zone. So somehow you are able to express your velocity profile based on a wall normal coordinate, a non-dimensional y coordinate, right? So the idea here comes from that part, that I am going to use something like a length. Okay, we will call it mixing length, which is basically a wall normal coordinate. So the modeling idea here is that comes from this turbulent boundary layers, turbulent boundary layer where u plus is a function of y plus, where y plus can be considered as a length, okay, a mixing length, either a linear function of y plus or a logarithmic of y plus, right? So using this log-law region or the linear sublayer, we can construct a model now. So what we do is, now we say simply eddy viscosity also I would like it to be a function of y plus. That's why the name mixing length. But it has to be meter square per second. Dimensionally we have to construct something, right? So this can be, as I mentioned, it can be your L square and of course and a time scale, right? So for the L square I will like to call this a name L mix. Here L mix is your mixing length. So the model has what is called kappa y square, okay, kappa y square, and then a turbulent time scale is required. But here the only available turbulent time scale, not really a turbulent time scale, but some time scale, is basically your du bar by dy. This is giving you a time scale. But note that here this is eddy viscosity, here this is a turbulent term, at least you want it to be a turbulent term. You defined it as turbulent viscosity, but now this is purely a geometrical length scale, right? Geometry dependent term, and this is flow dependent term. So both are not turbulent here, unfortunately, right? But this is what you have access to. So one particular unknown nu t is replaced by two known things. You have access to mean velocity and its gradient. So I get dou u bar by dou y as a time scale, right? So this is your time scale part, and this is your length scale part, kappa y. So here kappa is the von Karman constant, which is equal to 0.41, and y is your wall normal coordinate, just a distance from the wall, okay, like this, y direction in a boundary layer. And the du bar by dy, this, as I said, this is your time scale here, right? So there are some advantages of this model, but mostly this model is no longer being used. It's a too crude approach to model turbulence. The first one you already has realized that you want a turbulent term, but now you have a geometric length scale and then a flow time scale, right? So this is becoming non-turbulent basically. The model works, it's simple, but it has more disadvantages than advantages here. So note, so you have model is too very basic. The main advantage you can say is that advantages, or one advantage I can think of is that you can generate initial conditions in CFD calculations. So when you initialize your velocity u, v, w, and then you are solving for pressure and everything, you need to give an initial condition in your CFD calculation, what it has to be. Usually we don't put it as 0, we make a guess. So then if you have a field nu t, right, then you need to guess eddy viscosity, right? So you can use this formula to guess, to give an initial condition, right? So you can use this to guess initial conditions, okay? Model can be useful to give initial condition. In CFD simulations. That's an advantage. Disadvantage, of course, are many. As I said, the model is relying on flow and geometric scales, okay? Turbulence term is modeled based on a geometric and flow scale, not really a turbulent quantity at all, right? Yes, and another disadvantage, anybody can take a look at here, one of the biggest disadvantage here, that is there for all eddy viscosity models, okay? So whenever you construct a model, this should not be working only for one type of flow, as I told you, right? The model should be fairly working for many types of flows, and also it should be giving reasonable accuracy. It should be easy to implement in your software, and it should be numerically stable, right? So the schemes that you use should be such that it should work and code should not crash. So all these things, there are many ways the model can be popular. So now, is this model applicable to other classes of flows? For example, let's take a jet flow. Do you have y coordinate here? a wall normal coordinate, right? What about flow over a bluff body, or let's take a plume, or you take a mixing layer, right? In generic class of flows where you have to search for a wall normal coordinate which does not exist here, right? And even if you give for a bluff body, you can say, okay, there is a surface, I will use y as a wall normal coordinate. It will give erroneous values because there's hardly any boundary layer downstream. Only upstream you have some boundary layer development. Downstream it is all flow separation and turbulence coming in. So this is not applicable to all kinds of flows here, right? So works only for boundary layers. So what about jets, wakes, mixing layers, plumes, all these things? That is, what is y in those flows? Therefore, it's only specially made only for, let's say, a boundary layer flow. It doesn't even work for other flows, so you cannot even use it. I'm not even talking about accuracy here. Therefore, all zero equation models are become least popular. Today nobody uses it. The only use you can say is that you can use it for generating initial conditions. So some value is there other than 0, at least something is there to start with for your calculation. Okay, so we'll move to before this we would like to see whether model behaves physically. For example, eddy viscosity, this is a turbulent parameter. So now what will happen to turbulence close to the wall? Even in a boundary layer, it's become 0, right? The Reynolds stresses, if you are modeling based on eddy viscosity has to go to 0. It is fully viscous. In the linear sublayer, it's viscous dominant flow. So on the wall, what happens at y equal to 0? So you need to see, for example, at y equal to 0, what happens to this nu t value? According to the model, mu t exact has to be 0, right? So I can write it here. So at y equal to 0, nu t has to be 0, right? But according to this model, what will this be? Y goes to 0, right? So y going to 0 will make this, that is kappa y is equal to 0. So this is completely fine, right? And if you take a boundary layer, what will happen to when you go to free stream eddy viscosity? What should that be? Again, eddy viscosity has to be, there is no, in free stream there is no turbulence, right? Unless you have some value. Let's say there is no free stream turbulence, you are going to free stream conditions u infinity, then there is no turbulence. So eddy viscosity has to be 0. Is it giving this at very large y values? See, this is nu t is 0. Nu t is essentially 0 here because your kappa y is 0, right? That is kappa y is 0. So at y very large distance, right? At y very large, far away from the wall, then how will nu t be 0? Exactly, nu t is still 0. That's because your gradient goes to 0. So model is intact. Now they have thought about this. That model falls back to physical values on the wall, far away from the wall. Okay. Only problem is it works for a boundary layer. So now we don't discuss one equation now. We'll come back to that. I'll go to 2 equation model. It's much more easier to construct a 1 equation if you already construct a 2 equation. As the name says, there are 2 equations. That means there is actually 2 transport equations here, as against the 0 equation, right? 2 equation mean 2 transport. So when we go here to do transport. Now, first thing, as I said, we would like to address eddy viscosity. In the Boussinesq, we already use Boussinesq to close the Rance equation, but nu-t and k is still an open-ended question. So, we started attacking eddy viscosity now. So, we would like to see what nu-t will be in a 2-equation model. And mu-t, as I said, is a turbulent quantity. So, we want it to be based on some turbulence quantities. Okay. So, we will take up, for example, the u. I would like to model this as square root of k. It is square root of your turbulence kinetic energy. Right, turbulence kinetic energy, square root of k. So, now a turbulence term is included. This is a turbulence term. So, this is good. The velocity scale, it is addressed. Unlike previously, we are using flow time scale and geometric length scale. At least now I am thinking of using a turbulent quantity. This has two purposes. One, I am modeling eddy viscosity based on a turbulence quantity. Another thing, in Boussinesq, there are two unknowns, nu-t and k. If my nu-t is based on k, then that is also a great idea, right. So, in Boussinesq, hypothesis, right, nu-t and k are unknowns. Therefore, by modeling nu-t based on k is a good idea, right. So, one of the scale is set. Now, we would like to introduce another scale, a time scale here. Okay, I will put up a turbulent time scale, which is simply the ratio of k over epsilon. If you recall, this is meter square per second square and epsilon is meter square per second cube. Okay, epsilon is the dissipation rate of turbulence kinetic energy. It is the rate at which the k is changing. So, it will have the same unit as dou k by dou t, is same as epsilon, right. So, it is meter square per second cube. So, this is giving me a turbulence time scale, right. Again, this is a turbulence term, okay, turbulent time scale here. Turbulent time scale, but of course, it is not associated with a particular eddy, because k and epsilon is statistical. It is representing all the turbulence that is inside the system. So, we do not know, it is only on dimensional grounds we can say that the unit comes to a second, and therefore, this is a turbulent time scale, and u is of course, or square root of k is the turbulent velocity scale. Okay. So, now if I use these two, I can construct what is nu-t, right. So, I can say now nu-t, I would like this to be equal to, I want this to be function of k and epsilon. So, this forms the basis of what is called k epsilon models in the under the class of eddy viscosity models, a 2-equation problem. So, now nu-t is equal to a model constant comes in. I will tell you what this C mu becomes later. Let us take C mu k epsilon, but we need dimensions to be exact, correct. Mu-t has to be meter square per second here, right. So, we want that to be same as on the other side as well. So, how do I get this? When I want to make dimensions to be correct on both sides, this is meter square per second. I want here also, I want it to be meter square per second. How do I do this? Sorry? Dimensional analysis, right. So, using dimensional analysis. Okay, so I have meter square per second on the left hand side. On the right hand side I have meter square per second square A, meter square by second cube to B. So I get two equations, 2 equal to 2A plus 2B, that's for the M, and for S I get minus 1 equal to minus 2A minus 3B. Okay, so two simultaneous equations. So if I get rid of that, I get easily B is equal to minus 1. Substituting it back, I get A equal to 2, right? Let me write it. I get A equal to 2. So therefore, what does this yield? The model now will be nu t is equal to C mu k raised to 2 k square over epsilon. This is the expression used in the so called k epsilon eddy viscosity models. Mu t is computed using C mu k square by epsilon, but of course we still do not know, or at least we have not touched upon what is epsilon, how it is modeled, how k is modeled, how C mu is modeled. At least we have got an expression here, right? So what is C mu, how to compute k, how to compute epsilon, these three I need. So in the Boussinesq, nu t is solved at least. Even in the Boussinesq I need k, turbulence kinetic energy k. So if I am going to find out a way to compute turbulence kinetic energy k, that will solve the purpose for both nu t and k. In addition, of course, I need to figure it out what is C mu and epsilon. Okay.